Morning, everyone. Today is day 18 of Math 133. We're going to cover the Chapter 8 review today. That's going to start on page 471 in your course pack, 471. Um, and the lecture note that's being assigned is 9.1. Um, so uh, we're going to go through chapter 9 a little slower than we've gone through some of our other chapters. Some of our chapters we've gone through at like blazing fast speed. But chapter 9 some is a lot of information. It's not necessarily a lot of information. Um, it's a little more complicated, I guess. So it's not a ton of information, but chapter 9 is about confidence intervals. And so sometimes people struggle with that. So I'm going to make sure that we uh, all are getting the concept. Okay, so we're going to start working on the chapter 9 notes, but you can see that the chapter 9 review is not for like another week and a half. Okay, so anyway, but uh, Tuesday is our candy project. So make sure that you've purchased some M&Ms and some Skittles. Um, so you'll need to make sure that you have like 3 ounces or so of 3 ounces or more of M&Ms, and same with Skittles. Okay. Um, we're going to use that data from the Candy Project for the Chapter 9 project, which is going to be next week on Thursday. We'll also be using it for the Chapter 10 and the Chapter 11 project. So that's important data. So make sure you've got your candy ready to go. Okay. Um, okay, but for today, we are going to be starting on page 471 in your course pack for the Chapter 8 review. Um, so just like with our other worksheets, I'm going to give you some hints. The hints will be a little sparse today, I think, because Chapter 8 doesn't have a ton of like exercises and stuff. Chapter 8 is about the central limit theorem. Okay. And you don't necessarily need to know like the ins and outs of what that means. Um, Really what chapter 8 is going to allow us to do is it lets us use the normal distribution when we are looking at chapter 10, 9 and 10 and 11. Okay. So chapter 9, 10, and 11 are about confidence intervals and hypothesis testing. Okay. And so because of the central limit theorem, because it exists, we will be able to be looking at the normal distribution for all of that. Okay. But anyway, so um, for chapter 8, uh, um, fill in the table with the appropriate symbols. We've been using these symbols throughout the class, so I'm gonna let you guys fill all that in. Okay. Number 2, you can find information about this on page 183. Okay. Um, so let's skip to page 472. Sports analyst gathers a random sample of NBA players from the 2024 to 2025 season, records the number of games played. Summary statistics from their sample is shown here. Calculate the standard error of the sample mean. So that you'll find on page 184. And I'm actually going to pull that up right now. So page uh, 184 is here. Let's see if I can get it over there. All right. So in your course pack, page 184 is the central limit theorem for means. Okay. And we said that we don't necessarily need to understand like the the proof behind it or the all the details behind it, but we do need to understand some of it. Okay. So the central limit for theorem for means, right? This is an important theorem. This is something that on Tuesday I was excited about that this was something that we could use, and it was an interesting result, right? So, what the central limit theorem says is as long as you meet these conditions, and we'll talk about the conditions in a second, but as long as you meet these conditions, then the distribution of sample means will have a shape that's approximately normal. Okay, that's the key concept. Okay, now the center of that distribution of sample means will be the same center as your population mean. Okay, so in other words, the mean is the mean. Okay, so we're good. So whatever the population mean is, when you take a bunch of samples, you can use those samples and you'll be uh, able to approximate what the population mean is. Okay. The spread, though, is what we need for this question, question number 3 in our Chapter 8 review. The spread is called the standard error of the means. Okay, so here's our formula, the SEX bar formula. So yeah, I don't know if that helps you memorize it or not, but SEX formula here is the standard deviation of the population or the sample. So it's the standard deviation divided by the square root of the sample size. Okay. Now this formula is not in your exam notes packet, so maybe it's going to be an important one to write down on your 8.5 by 11 piece of paper. Okay. But you don't need to write the whole thing. Okay. So I'm just going to write SEX bar equals standard deviation divided by the square root of the sample size. Okay. So if you have the standard deviation and you have the sample size, you plug it in here, put it in Desmos, and you'll be able to calculate your standard error. Okay. So this is what I would recommend writing down on your 8.5 by 11 piece of paper. Make sure you have this. Okay. You are allowed to write on your exam notes packet. So if you want to write in your exam notes packet, you can do that too. Okay. There you go. Now, this is not done. That's just the formula, right? You got to actually do the math. But okay, so now let's. So for question number 4, average BMI for adults is this. Standard deviation is this. 72 random adults. Verify the conditions of the central limit theorem for means are met. So now we're going to go back and we're going to talk about the conditions. Okay. So the central limit theorem says that as long as you meet these conditions, then your distribution of sample means is approximately normal. Okay. Just like any theorem, so probably the theorem that most people in the class are the most familiar with is the Pythagorean theorem. The Pythagorean theorem is a squared plus b squared equals c squared, and it's been around for thousands of years, and it's a very important concept in geometry. I would say that it is the most important theorem in all of geometry. You can use it for a lot of different things. However, there are certain conditions where you can use it or not. In order to use the Pythagorean theorem, you have to have a right triangle. Okay. Now that's the only condition for that one, which is nice. For the central limit theorem, similarly, there are conditions on that. I don't know if there's other theorems you guys know of. Probably haven't worked with the fundamental theorem of calculus, but that one, there's certain conditions that you need to meet in order to use it. Okay. For this one, the conditions are random, independent, and normal. And we are going to be looking at those throughout chapter 8, which is where we're, introducing this concept. But we are also going to be talking about those conditions for chapter 9, chapter 10, and chapter 11, because in order to do the stuff in chapter 9 for confidence intervals and hypothesis testing in chapter 10 and 11, we have to satisfy that the central limit theorem applies. Okay. We don't have to show that it's the right triangle. We have to show these conditions: random, independent, and normal. Okay. Um, okay, so I'm going to put that right here. Verify the conditions of the central limit theorem are met. So we have to check random. We have to check normal. Oh, sorry, independent. Shoot. The order doesn't matter, but we're going to do it in this order just because makes it easier to remember. So random, independent, and normal. Sorry. Okay, so random just means that each observation is collected randomly from the population. You have to take a random sample. Okay. In chapter one, we've done a lot of definition stuff where we talked about biases in samples, right? Biases will make it so that uh, your your sample does not represent your population very well. Okay. If I was trying, for example, to figure out, who's going to win the next presidential election, okay, I can't go and ask every single voter, who are you going to vote for? That's going to take way too long. There's hundreds of millions of people in the US, right? And so instead we do a sample. And that's what they talk about with these polls, right? They do a poll where they'll ask like 1,000 people or 5,000 people or whatever, okay? They ask a whole bunch of people, who are you going to vote for? And that is close enough that sometimes you can make a pretty good estimate or pretty good prediction, okay? Um, However, if you aren't doing a random sample, then you're going to have bias in your result. Okay. In other words, if I only asked people in California who they're going to vote for, then you're going to say, oh, well, the Democratic Party is going to win because California is well known to always, at least for the last, 10 elections or so, to select the Democratic Party. All of their electoral votes go to them, right? Uh, Same thing if I was to ask, Alabama. Alabama is well known at being a red state. They usually almost always are choosing Republican candidates. Okay. So I need to make sure that when I'm doing my sample, I am doing a random sample where everyone has equal opportunity of getting selected. I don't want to bias it in any way. Okay. So that's the key is each to make sure that's random, each member of the population has to have equal chance of getting selected. Okay. Now for our class, random is going to be the easiest one to check. You basically just have to make sure that the word random is somewhere uh, in the wording of the question. So so we say yes, it's given. It's right there. Found it. Okay. That's all I have to do for our class. In practice, in the real world, randomness is the hardest of these three conditions to meet. Okay. The independent part is make sure your sample is not too big. The normal part is make sure your sample is not too small. Okay. So as long as your sample size is big enough and not too big, then you're good to go. Okay. But so for our class, we're going to have to do some math for independent and normal. But I want it to be clear that even though random feels like, yeah, it's given, we're good. Okay. In practice, that is definitely the hardest to do. I'll continue my example with the presidential election. If I wanted to uh, predict who's going to win the next election, I need to do a random sample. So that means I need to take the, you know, 300,000, or sorry, not 300,000, 300 million voters in the US, and I need to randomly select, I don't know, let's say 1,000 of them. Okay. And then I need to go ask them who they're going to vote for. Now, in order to make sure that everyone has equal opportunity of getting selected, I need to select people from all across the US, which means that even still, I'm going to have to travel to like a bunch of different states, probably every single state, and ask these random people, like, uh, who they're going to vote for. And if it's random, that means everyone has equal opportunity to get selected. So if you randomly select this guy and you have to go to his house and ask him, who he's going to vote for, he might not want to answer. He might not answer the door. He might be like, I don't participate in polls and surveys and stuff like that. So, um, can you just, not count his vote? No, if you don't count his vote, then that means that he is changing your result because it's no longer an independent result. Okay. So anyway, so the randomness is actually the hardest thing. So most of the time you can't do a random sample. Most of the time you have to do some kind of other sample where you could do a stratified sample, or you could do, uh, we've talked about a couple of different sampling methods in the chapter 1 vocabulary stuff. Um, but anyway, so all of those are approximating randomness, but they're not actually equal. They're not actually random. Okay. There is small bias here and there. Okay. So anyway, um, that all said, for our class, we just have to make sure the word random is in the word problem and we're good to go. Next is independent. Now, independent is the easiest one to check. Independent, you just have to make sure that your sample size is not too big. Okay. So to check that, you want to make sure that your sample size, which is lowercase n, is less than 5% of the population. Population is capital N. Okay. And as long as this inequality is true, then you're fine. Okay. Um, Most of the time, making sure your sample size is not too big is very easy to do. Okay. And checking it with the math is probably going to be pretty easy to do as well. Okay. Now, this formula right here, you can use this one, or you can use what it says here. The population must be at least 20 times larger than the sample size. Um, 20 times 5% is 1. So in other words, if I wanted to move this 5% over to the other side, I could multiply both sides by 20. And so there's a different formula that you could use, which is 20 lowercase n has to be less than capital N. Okay. So this would be another good formula to write on your 8.5 by 11 piece of paper. Okay. You can do it this way, or you can do it with the decimal 0.05, so 5%. These mean the same thing, because this one I just multiply both sides by 20 and I get 20n is less than 1 capital N. Okay. I'm going to use this one, and just because people like whole numbers, they don't like decimals. Okay. So for our case, for question number 4, what is lowercase n? What was the sample size? Read through question 1. Yeah, Yvette's got it. 72. Okay. What was the population size? 250 million. All right. Right. 72 random US adults. That's our sample size. All US adults would be 250 million. That's population size. In your calculator, please, 20 times 72. 1440 is 1,440 less than 250 million. Yes, it's way less, right? So yes, for sure, right? Yes, of course. Okay. Most of the time, your sample size isn't even close to your population size. The whole point of taking a sample is your population is too big. If your population is too large, you can't measure everyone. You can't measure everyone's BMI. You can't ask everyone in the US who they're going to vote for. It's going to be too expensive. It's going to take too long. You can't check everyone. So the whole point of doing a sample is we select a random sample that we can measure that, and the mean of that sample is going to be extremely close to the actual population mean. Okay. We can't measure the population mean, but we can get really close using a sample. Okay. So if that's the case, then selecting a giant sample defeats the purpose. If you can already measure, you know, 50% of the people in the US, then it's just a little bit more work to measure everyone. Okay. The whole point of taking a sample is usually your sample size is going to be tiny compared to your population size. So independent usually is a very resounding yes. Okay. Um, Now, by the way, I will point out that this formula is not the same formula that you will find uh, if you look up central limit theorem like on Wikipedia, or if you're on like Google or something like that. Okay. So if you, we're using this because this is a little bit stricter conditions than what you might find on Google. Okay. What you find on Google is still fine. Or no, sorry, let me backtrack that. If you're using the formula that's on Google, you will not get points for this. Okay. Um, what we're doing also matches what is still going to satisfy what you find on like Google or Wikipedia or whatever AI system you're using. But it's a little stricter because it's going to make it more accurate. Okay. So make sure you're using this or this. Either of these is fine. Okay. Make sure you're using the formulas from the class. Okay. Is that fair to say, Elaine? May I describe that okay? Oh, she had to step away. She's got a delivery. Okay, we're good. All right. The last one was normal. Okay, so when we say normal, I don't mean that the population is normal. I if the population distribution is normal, with no outliers given. So in other words, if we have a quantile graph that we can look at, we can say, okay, well, the population's normal. Um, but you'll remember when we were looking at the Chapter 8 project on Tuesday that when your sample size hit 30, it didn't matter what shape your original population was. If your original population was skewed left or skewed right or some other crazy shape, if your sample size was large enough, then the shape for your distribution of sample means was normal. And the cutoff we said was around 30. Okay. So for means, we need to make sure that our sample size is bigger than 30. So let's see what that looks like here for our uh, question number 4. So we need to verify that n is greater than 30. So in this case, our n was 72. So 72 is bigger than 30. Is 72 bigger than 30? Yes, it is. So we are good. Okay. So since I have three S's, yes, it's random. Yes, it's independent. Yes, it's normal. Then that means that the conditions of the central limit theorem for means have been met. Okay. We're going to be doing these three steps a lot throughout the rest of the class. Okay. Um, Now, you'll notice that the formula that's listed in the course pack has greater than or equal for uh, or sorry, less than or equal for independent, greater than or equal for normal. Um, and I've dropped the equal. And I've said this already. I'm going to kind of play a little loosely with whether I put the less than or equal or not. If you just write less than, I'm fine with that. Um, if you just put greater than for the normal one, I'm fine with that. If you put the equals there, that's fine too. Um, if your sample size is equal to 30, technically you have satisfied the conditions of the central limit theorem, but 30 is the lowest. Even then, though, that's not a great sample size. The larger your sample size is, the more accurate your results are going to be. Now, obviously, you can't go above 5% of the population size, right? That's one of the other conditions. But as I said a second ago, we're never going to get even close to that. Okay. For independence, like your sample size is going to be tiny compared to the population size. Okay. So, um, when we're talking about selecting a sample size, it's very important that you select a sample size that's big enough. If I only talk to 30 people and ask those 30 people, who are you going to vote for in the next election? Okay. That doesn't sound like a lot of people. Hopefully you agree with me. Like if I talk to 30 random people, is that really a good estimate for the entire population of the US, all the people that are going to vote, all the hundreds of millions of people that are going to vote? um, yeah, it really doesn't sound like it is, right? You really want to talk to maybe 1,000 people or more. That's a reasonable sample size. A sample size of 30 technically is allowed, but it's not going to be super accurate. And we're going to see that as we go through the next couple of chapters, where if you use 30 as your sample size, yes, you can construct a confidence interval, but your confidence interval is going to be massively huge and it's going to be useless. Okay. So technically greater than or equal to 30, but being equal to 30 is not the best. So that's why I'm going to just kind of ignore that and just say, okay, it's got to be strictly greater than 30. Even 72 is not a great sample size. If I was trying to measure the uh, BMI for all the adults in the US, I probably would be able to measure more than 72 people, right? I don't know. Anyway, um, okay, so that's all that. Once you um, have satisfied those three conditions, then that means you can use the central limit theorem, which means you can talk about the shape, the center, and the spread. The most important piece of that is that the shape is normal. So describe the sampling distribution of the sample means, give the shape, center, and spread. Okay. So the shape is normal. Okay. The center is going to be the same mean as your sample. So the average BMI for adults in the US is 30.7. So the center is mean. So they write it as, this is crazy confusing in my opinion. They write it as mu sub x bar equals mu. What the heck does that mean? Mu is a mean and x bar is a mean. Mu is the mean of the population. X bar is the mean of the sample. So this is saying the mean of the distribution of sample means. What? That's confusing. I All that you need to know is that the mean of your sample is a good, not a good, an excellent estimate of the population mean. Okay. That's the whole point of doing the sample. I want to measure something for all the people. Well, I can't do that. There's too many people. The population's too big. Okay. Let's take a random sample and measure that sample and see what the average is there, and we'll use that as an approximation for everyone. Okay. I want to know what the average height of all the people in the US is. Well, I can't do that. Okay. I can get a sample of people, measure their heights, find the average of that sample, and it's going to be very, very close to the population mean of what is the average height of all the people in the US. Okay. That's the idea. So the center is whatever mean you had. The mean here is 30.7 kilograms per meter squared. Okay. So that's what we're going to write. Okay. Um, so you don't even necessarily need to write all of this. You can just write mu equals this, or you can just write it. You can just drop that and say that's 30.7. Because I find this mu sub x bar confusing. But technically that's what it is. That's what that means. All right. Lastly is the spread. So the spread is our SEX bar standard error equation, which we said is sigma x bar, which is the standard deviation divided by the square root of sample size, which is the standard deviation by the square root of sample size, which is the standard deviation divided by the square root of sample size. All these mean the same thing, okay? So you don't have to write this whole thing out. You can just write it as standard deviation divided by the square root of the sample size, which in our case, the standard deviation was 6.1. Sample size was 72. So let's see what that gives us. All right, 6.1 divided by. To do a square root, you type SQRT 72, and that is our spread. So 0.7, we want 4 decimal places, 0.7189. Okay. That is the standard error of the sample means, which is, and you need units on it. The units is kilograms per m squared. Okay. Don't worry. If you found that confusing, that's okay. I was, spouting a lot of theory and stuff. The actual calculation, the actual steps, random. You just check, make sure the word random's in there. Yes, given. Independent. We use this formula, plug in the numbers that we have. Normal. You just have to check that n is bigger than 30. Shape is always going to be normal. Center, you just write out what the mean is. And then the spread is the only part that you actually have to do any work. Use this formula here, and you're good. Okay? All right. So page 473. Um, so the central limit theorem um, for means is what we just talked about. Okay. But at this point, there's a second one, which is for population, or for proportions, which is down here on page 189. And it's very much similar to the one for means. Um, there's just some slight differences here and there. Okay. Um, so uh, we've been talking throughout the class about means, um, but then chapter 5 and 6, we kind of shifted gears and we started talking about probabilities, okay, which had nothing to do with means and medians and stuff like that. Um, probability, uh, and mean, like, they are two different concepts. Um, but instead of putting these into two different chapters where we talk about means and then later we talk about probabilities, or instead of even putting these in two separate classes, we're just going to combine them together into one thing. Okay. So chapter 8 is going to include information about means and probabilities. The same thing is going to be true for chapter 9 and 10, 11. Sometimes we'll be talking about means, sometimes we'll be talking about probabilities. Okay. Um, so uh, I've already started mixing those together, even in the examples that was giving a second ago, where a second ago I was asking, what's the average height of all the people in the US? Um, that's a mean. That's an average. You take everybody's height and you average them together, and that gives you the mean height. Okay. But then I was asking, okay, who's going to get elected the next president? That's not a mean. Okay. That's a probability. If I asked, who are you going to vote for? Your answer is going to be Republican or Democrat. Your answer is going to be a word. Your answer is going to be qualitative. If I asked you, what's your height? You would give me a quantitative number. I am 5'7" right? And I could take that number and I could add up all the other heights and divide by how many numbers there are, and I can calculate an average. You can't calculate an average Republican Democrat vote. That doesn't make any sense because who you're going to vote for is a qualitative number. And when we're talking about qualitative data, usually we talk about probabilities. Okay. What's the probability that this person's going to vote Democrat? What's the probability they're going to vote Republican? What's the probability they're going to vote, I guess, independent, right? So, um, but they're related, right? I can't measure everyone's height. I can't check who everyone's going to vote for. So I have to do a sample. And when I do my sample, as long as my sample meets certain conditions, I can use the central limit theorem to say that the shape of that distribution is going to be approximately normal. Okay. And the same thing will apply whether we are talking about means or probabilities. Okay. And that's why we're going to kind of interchange these together a lot. But as you're working through these problems, always pay attention to whether you are looking at means or probabilities. Okay. So instead of splitting them into two separate chapters, it's kind of, or two separate classes, we put them together into a single class, Math 133. And so you get bonus. It's basically two classes in one. So that's great, right? Anyway, the central limit theorem for proportions, as I said, is very similar to the central limit theorem for means. There's only two differences. One is on the normal part. You can't just say, well, n has to be bigger than 30. That doesn't work anymore because if your sample size is 30, or even if it's bigger than 30, even if it's like 100, but your probability is tiny, then that sample size will not work. Okay. Let me give you an example. Um, let's say that I'm an ad campaign, or I'm um, an advertising agency, and we're putting out this new ad campaign for, I don't know, some kind of cleaning product, right? And we want to test the effectiveness of our commercial. Okay. Well, I can't I can't, put out this commercial and ask every single person in the US, are you going to buy our cleaning product? Right. So instead, we could do a sample and we could say, okay, we put out this commercial and we talk to 1,000 people, or maybe only like 100 people. And we ask those 100 people, so you saw our commercial, are you going to buy our product? That sample size of 100 people or 1,000 people is not big enough. Because think about all the commercials you see. You see hundreds of commercials a day, right? We in America are inundated with commercials all the time. Do you buy a product every time you see a commercial? No, you don't. Do you buy a product 1% of the time? No, you still don't, right? There are a lot of commercials that you just completely ignore, right? A good commercial return rate is if 0.3% of the people who see your commercial buy your product. That's tiny probability. So if I show this to 100 people, one person might buy my product. That's not a big enough sample size to say whether my commercial is effective or not. Okay. Because if one more person buys my product, now I have two people buying my product. That's only one more person, but it's doubled the rate. Okay. So what I'm getting at is that when you're checking to make sure that your sample size is big enough, you can't just say it has to be bigger than 30. You have to make sure that n times p times q has to be bigger than 10. Okay. So if your sample size is huge and your probability is not too small, then you're fine. Okay. There's only two differences. One is that one. The other one is down here. Instead of standard error of the x of the mean, it's the standard error of the proportion. So p hat, which is now the square root of p hat q hat divided by n. Um, Technically, this is the same formula as the standard error of the mean. It's just that the mean is equal to the square root of p times q. Anyway, there's a different formula. Technically, it's the same. You don't need to know all that. Let's actually try one of these. Okay. Um, so page 473, you'll find information on this on page 189. Let's skip now to the last page, page 474. Um, let n equal this, p equals this, compute SE p hat. Standard error of the proportion is the square root of p q over n. So this is, again, a formula you're not going to see on your exam notes packet. So another formula you might want to write down on your 8.5 by 11 piece of paper. Now, there's two different ones here. One is PQ over N, and one is P hat Q hat over N. How do I know which one to use? It doesn't matter, okay? If you have P and Q, or sorry, if you have P, you can calculate Q, right? If you have P, use this one. If you don't have P, if you have P hat, use this one. You're never going to have both P and P hat. If you do, then there was no point in doing the sample, okay? The whole point of a sample is you can't calculate P. So in our case, we have P, so we'll use this one, okay? So I'm not going to include the hat here, but you can if you want, okay? Anyway, for question number 7, study found that 39.5% of U.S. teens have their driver's license. Verify the conditions of the central limit theorem are met. They are very similar to the one for means. We want random, independent, and normal. Okay. And then once you've checked those three, if you get 3 yeses, describe the shape, or sorry, describe the sampling distribution, describe the shape, describe the center, and describe the spread. Okay. All right. I'm going to stop the recording right here. We'll go back through and we'll fill out all these answers. Okay. But we're going to be doing these same kind of steps all throughout the rest of the class. Okay. So you'll get real used to doing them, and you'll be old hat at it. You'll be ready to go for when test day, when the final gets here. You'll be like, oh yeah, random, independent, normal. I can do that in my sleep.